So we're about to look at a final exam from Calculus 1, locally known as Math 1650 from the fall 2024. What a great vintage that was. Now, every final exam is a snowflake. It's special and it's unique. They're all slightly different from one another. So what we do here may or may not be similar to what you're going to see on your final, but definitely practice is important, so it's good to go through and do some problems. We're going to have 8 multiple choice, 5 long answers. Lucky 13 problems for us to do. Woohoo! And of course, as always, we're going to start by putting our name on it. Because if we don't put our name, we won't get the credit. All right, let's begin. Number 1. Find the limit as x approaches 1. X squared minus 5x plus 4 over 4x squared plus 4x minus 8. So what are we going to do? Well, what you do with every limit, plug it in first and let's see what happens. So when we plug in 1, right, pay attention, right? We're not going to let little tiny things get us. So we're going to 1. Well, upstairs we'll get 1 minus 5 plus 4. Downstairs, 4 plus 4 minus 8, 0 over 0, which equals more work. More work. Well, what are we going to do? Now, we could do it algebraically, but hey, we have one of our favorite tools. Ah, l'hôpital, mon ami. So if we apply l'hôpital, well, this will become a limit as x approaches 1. Take the derivative upstairs. So it's going to be 2x minus 5. Take the derivative downstairs, 8x plus 4. And what do we do? Well, we plug in 1. Upstairs, 2 minus 5. Not 0, so we're done. Whatever it is that's going to happen, it happens right now. 8 plus 4. And so that's negative 3 over 12, or negative 1/4. So the answer is negative 1/4. D. And we're done. Good. All right. Number 2. Which of the following expressions gives the derivative of f of x equals the square root of x squared plus 1? Now, what's going on here? Well, notice when we say following expressions, they're all a limit. So this is testing us of the limit definition of derivative. Now, there's 2 limit definitions. So they have the form limit as h goes to 0, f of x plus h minus f of x over h, or limit as z approaches x, f of z minus f of x over z minus x. Now, looking at what we have here, we see that they all have that over h form going for it. So we're in this version. So we start saying, okay, we need to have the limit as h goes to 0. That knocks out 2 options right away. Look at this very carefully. It's very small. I don't know if the resolution is good enough to see. But C and D both say limit as x goes to 0. So it can't be those 2. All right, good. Good. And now we say, okay, let's look at what's left. All of them have the same f of x piece, so it's all going to boil down to what you see here. So, given f of x is the square root of x squared plus 1, what is f of x plus h? Right? That's the only thing that we don't know. So the question is, which one of these 3 pieces has the right form of f of x plus h? Now, how do you find it? Well, when you think of a function, it's a machine. It says take the input and do something. Now, this machine says square whatever you put in, add 1, then take the square root. So if we put in x plus h, you square what you put in, add 1, take the square root. So we're looking for an expression which has this. Now, x plus h quantity squared is not x squared plus h squared. that's something a little bit different. There's that sort of middle term, that 2xh. This doesn't even have an x in it. Hopeless. But look here, x plus h squared plus 1. Perfect. F of x plus h minus f of x over h, limit as h goes to 0. There's our answer. Okay, that's 2 down. Let's keep going. To number 3. Suppose f of 2 equals 5, f prime of 2 equals 1, and h of x is 3x times f of x. Find h prime of 2. So what are we testing on here? Well, we're testing taking the derivative of h, which is a product of 3x and f of x. So we say, okay, h prime of x, product rule, the derivative of the first times the second, plus the first times the derivative of the second. All right, so product rule. Now plug in 2. H prime of 2, that's 3 times f of 2, plus 3 times 2 is 6, f prime of 2. So that makes 3 times 5 plus 6 times 1, which is 15 plus 6, or 21. C. Good, good. Now, I will say we probably could roll out D pretty quickly because this has multiples of 3 everywhere, and 11 is not a multiple of 3. But all right, that's number 3. Which brings us to number 4. We're cooking. Oh my gosh. Maybe we'll have enough time to do this test twice. No, once was enough. All right. A particle's position at time t greater than 0 is given by t cubed minus t squared plus 1. So there's our position. When the particle is at rest, that is to say velocity equals 0, what is its acceleration? So, what do we have? Well, we're told s of t, and we use s for position, t cubed minus 2t squared plus 1. And we have something about velocity and something about acceleration. So let's get those two functions. Velocity is the derivative of position. It's how position changes. So take the derivative, 3t squared minus 4t. Acceleration, well, that's the derivative of velocity. It's also the second derivative of position, which in our case is 6 times t minus 4. All right, now the stage is set. We are told we want to look at it when the particle is at rest. So velocity equals 0. So we set this equal to 0. So we have 3t squared minus 4t equals 0. Now you can factor a t out. So this becomes t times 3t minus 4 equals 0. Now, that leads us to two possibilities. T equals 0, or 3t minus 4 equals 0, which is another way of saying if you add 4 divided by 3, t is 4 over 3. Now, which one is the one we want? Notice they added something here. They said 4 time greater than 0. Well, notice this is a time greater than 0, but 0 is not greater than 0. So this one, gone. So we are going to plug 4/3 in to acceleration. So we're going to get 6 times 4/3 minus 4. Well, 3 goes into 6, so that becomes 2. 2 times 4 is 8, and 8 minus 4 is 4. And so our answer, what is its acceleration? It's 4. All right, and there we go. Okay, we're halfway through our multiple choice. Let's go to number 5. Let a be a constant, and f of x is tangent pi x to the a plus a squared. If f prime of 1 equals 2 pi, find a. All right, let's think about this. What do we have? Well, we want to take f prime, so we take the derivative, f prime of x. So here we'll use our chain rule. Derivative of tangent, secant squared pi x to the 8, leave the inside alone. Times that by the derivative of the inside. Pi is a constant, and the derivative of x to the power a is a x to the power a minus 1. Now what's the derivative of a squared? Be careful. You want to say 2a, right? Very natural, and I'll give you a spoiler. D and E are what would happen if you chose 2a. What is the derivative of a squared? 0. Why? Because there's no x. It's just a. A squared's a constant. So, right, this piece right here, this is a constant. And the derivative of a constant is 0. So this is a trick that they sometimes do. And I hate to use the word trick, but really it's just sort of like, are you paying attention? Things like a squared, constant squared, constant. E to the a, constant, right? So don't fall for these tricks. Know what they are. Now, what do? We plug in 1. F prime of 1, well, we get 1 to the a is 1. So we get secant squared of pi times pi a, and 1 to anything is 1. All right, and all that needs to equal 2 pi. Now, what is secant squared of pi? To answer that, start with cosine. Cosine of pi is minus 1. So secant of pi, you flip that upside down, and you get minus 1. Now you square that, and the answer is secant squared of pi is 1. So we really have, pi times a equals 2 pi. Pi's cancel, a should equal 2. And there you go. Now, as I said, if you took 2a, you would have gone like a pi a plus 2a equals 2 pi, which would have gotten you to d. If you've forgotten things like maybe you forgot to take the pi, you would get other similar wrong answers. So one of the things that happens when they write tests, and you can think that's mean or not, is they say they know common wrong answers, right? And so you want to be confident, not that you say, just because you got an answer doesn't necessarily mean it's the right answer. Make sure you're doing the process right, because they know common mistakes. So clean up your mistakes, which a lot of time means slow down. Take your time. Breathe in, breathe out. You can do this. You can do this. All right, let's keep going. Number 6, the absolute maximum of x minus 1 over x squared plus 8 on the interval 0 to 10 occurs at, and then we have some choices here. Now, we can quickly roll out C, because negative 2 is not between 0 and 10. So, not even a possibility. And look at this. There's no problems. There's no like blowing up going on. Denominator is always positive. So we have 2 options right now. One option is we plug in each of these numbers and we just say, hey, let's look how big they are. And the other option is to say, well, let's just go through the process. I'm not claiming one is better than the other. Do what works for you. So I'm going to go ahead and just do the process. So we're testing on absolute max and min. And for that, you have to channel your inner, we're making a list, we're going to check it twice. We're going to find out which points are nice. always include the endpoints in there. Okay, so 0 and 10, endpoints, those are always places where we could have a max or min. Now take the derivative, quotient rule, low d high. So x to our place 8 times 1 minus high d low, x minus 1 times 2x, all over the bottom squared, low squared. Now, never undefined. We don't have a 0 going on downstairs. So we say, look, set the numerator to 0. So that's really x squared plus 8 minus 2x squared plus 2x equals 0. And, okay, so minus x squared plus 2x plus 8 equals 0, or x squared minus 2x minus 8 equals 0, which factors as x minus 4, x plus 2 equals 0. And that gives us two critical points, x equals 4, x equals negative 2, but we're in the interval from 0 to 10, and so we can knock out negative 2. We already talked about that. But that's one of the reasons why you see negative 2 was listed there. Oh. Okay, so on our list, 0, 10, and 4. Endpoints and critical point. Now what do? We plug them in. But we don't need to plug in a 0 because that's not even an option. But it's not hard to plug in 0. That's negative 1 over 8. If you plug in 10, we get 9 over 108. Okay, well, that's a number. It's the same as, you can divide top and bottom by 9. And this is 1 over 12. And if you plug in 4, well, what do you get? You get 3 over 9 plus 8 is 17. And you say, okay, how does 1 over 12 compare to 3 over 17? And the answer, well, 3 over 17 is bigger. It's a larger value. And I say, how do you know that? Well, 1 over 12 is smaller than 0.1. 3 over 17 is bigger than 0.1. So the punchline here, x equals 4. All right, good. Okay, let's go to our next problem. Number 7. Find the integral of 2e to the x plus 3 quantity squared dx. Oh my goodness. There's so many ways we could get this wrong. And, okay. Now, how do you do integrals? There's sort of a hierarchy. One, maybe it's one of like 10 integrals that we know by heart. And you're probably like, there's 10, Steve. That list seems pretty short. Yep, there's like 10. It's not a very big list. And so, okay, so let's assume we've exhausted that. And because 2e to the x plus 3 is not on that list, then I tend to look for, is there an algebra or trick thing I can do? Or is there a substitution I can make? Now, here I say, oh, wait, no trick, but algebra. Algebra. Oh, I think there's some algebra you can do here. Algebra. Algebra. Yes, we've got the energy. Yes, we can do it. Now, what's our algebra here? You see that square? We're going to square it. And we're going to do it carefully. So what do I mean by we're going to do it carefully? Well, let's take 2e to the x plus 3 times 2e to the x plus 3. So we get 4e to the 2x. That's what happens when you multiply 2e to the x times 2e to the x. Then a 6e to the x and another 6e to the x, giving us 12e to the x, and then a plus 9. So in other words, we just foiled here. Yep, we foiled their plans to trick us because we will not go down. We will figure it out. 4e to the 2x, 12e to the x, plus 9. All right, now term by term, right? Because it's linear. So you say, look, now we can break it up. So we couldn't break it up before because it was inside the square. Now that it's not inside the square, we can break it up. What's the integral of 4e to the 2x? Well, it's 2e to the 2x, right? Because you're going to bring a 2 down. Divide by 2. Integral of 12e to the x is 12e to the x. Integral of 9 is 9x and plus c. And so we see 12e to the x plus 9x plus c. Yes, what's the right term? C. And again, lots of potential things where it's easy to forget. Like, oh, maybe if I brought the 2 not to the denominator but the numerator, I get an 8. Or maybe if I forgot to bring the 2 down at all, that would give me a 4. Or maybe it's just like, oh, hey, you add 1 and then divide. Then that gives me 8, right? They can spot common errors. So don't go so fast that you make silly mistakes. Don't leave any low-hanging fruit on the tree. Give yourself time. You can do it. There's plenty of time. Number 8, our last multiple choice. Using the substitution, u equals 2 minus x cubed. Okay, so they gave us the substitution. That's going to help. We have that the integral from 0 to 1 of 6x squared square root 2 minus x cubed dx is equal to one of these choices. All right, so we need to figure out which one of these choices it is. We'll do a couple of things here. What do we see? Well, this part right here, that's obviously going to become our u. No big surprise. U equals 2 minus x cubed, so let's do our du. So take the derivative of 2 minus x cubed minus 3x squared dx. You say, well, what do we have here? Well, we have a 6. Well, how do we make a minus 3 into a 6? Well, what we can do is use our fancy technology here called multiply by negative 2. So minus 2 du is 6x squared dx, right? So 6x squared dx is going to become minus 2 du. So what do we have? Well, we have that this becomes integral of minus 2 du, right? That's our 6x squared dx minus 2 du, square root of 2 minus x cubed, square root of u. Okay, we're looking promising, looking very promising. And then we have our bounds. Okay. Now, if we just stopped here, by the way, do any of these look right? These have 3's, not 2's. This is just crazy. What were they thinking? Well, there is actually a thought process here. It wasn't just random. But now, it looks like B is the right answer. If you put 0, 1, it's exactly that, right? But we're not falling for that trick, right? We're going to get this one. Because remember, these 0's and 1's aren't just random numbers. These are x bounds. X equals 0 to x equals 1. We need u bounds. So let's update our u bounds. When x equals 0, what does u equal? Well, 2 minus 0 cubed is 2. When x equals 1, 2 minus 1 cubed is 1. So the bounds are not right. That says 0 to 1. You might say, well, wait, that says 1 to 2. But what can you do? You see, you can use advantage of the fact that orientation matters. In other words, you see how the bounds are in the wrong order, and there's a minus sign. Well, when you flip the order of the bounds, you change the sign. So this is the same as flipping the order and dropping that sign, meaning C is the correct answer. All right, and that's it for our multiple choice. And on multiple ones of these problems, little tiny things. You know, oftentimes multiple choice you think of as like, oh, we're testing a big idea. But oftentimes it's very small specific steps where if you're not careful, it's easy to make a small mistake. So pay attention to details. details matter a lot in these kinds of computations, and you want to give yourself all the advantage that you can. All right, now that we've made it through our multiple choice, let's go and do long answer problems. We'll start with number 9. An ellipse is given by x squared minus 4x plus 4y squared plus 4y equals 5. And part A, find an expression for dy dx in terms of x and or y. Now, what setting are we in? Right? Because oftentimes if we can figure out the right setting, then it's like, I have an idea of how to proceed. So what setting are we in? The answer is, this is implicit. Now, why do I say implicit? Well, because we don't explicitly have y in terms of x. We have a relationship between x and y. Now, how does one solve a problem that's an implicit differentiation? Well, the answer is we say, we imagine that we do have y as a function of x. So that's the key. We say, I don't know what that function necessarily is, but I imagine that it does depend on x. And put another way, we would say, this looks like x squared minus 4x plus 4. And then I'm going to say y of x squared plus 4 y of x equals 5. That's what we're thinking, right? This is what it means when we think y is a function of x. And now the idea is, let's take the derivative with respect to x. So we're going to take the derivative of both sides with respect to x. And so some of them are more straightforward. Derivative of x squared, that's 2x. Derivative of minus 4x, that's minus 4, plus 4. Now here, use your chain rule. 2 comes down, then you get y to the 1, so that's y, times the derivative of y. Now, what's the derivative of y? The answer is the derivative of y. Yes. And I'll go ahead and write it as dy dx, just to emphasize, because we're taking the derivative with respect to x. Plus 4, and the derivative of y with respect to x, which is 4 derivative of y with respect to x, equals, and don't forget, you got to take this derivative as well. Take the derivative of both sides. Because if both sides are equal, both derivatives have to be equal, and the derivative with respect to x of 5 is 0. Now, after you've taken that derivative, you go into your your hunter-gatherer phase. And you say, well, on these two pieces here, they both have a dy dx. So you move things around. You put the dy dx terms next to each other, and you say, well, dy dx times, this will be 8y plus 4. And then the other pieces, you move across. So that would be equal to 4 minus 2x. And then we can divide and say, well, dy dx is equal to 4 minus 2x over, well, I'll write it as 4 plus 8y. And divide both top and bottom by 2, everything's even. So we get 2 minus x over 2 plus 4y. And there we go. That's it. Wow! Woohoo! Because what did we do? We have an expression for dy dx in terms of x and or y. Nice. Now you might be wondering, if I had solved for y and then do this, would I have gotten the same expression? Yes, but it would have been miserable. And this actually is a little bit more powerful, because technically there's 2 curves for y, because it's an ellipse. So there's like a top half and a bottom half, and it would just be a big headache. So if you have an expression where you have both x's and y's intermingled, go with the implicit. That's the way you're going to succeed. All right, there's a part B. Find an equation for the tangent line to this ellipse at the point 3, 1. Okay, so we're after a tangent line. And whenever we see tangent line, or in line in general, what do we know? We know we need two things. We need a point, and here's our point. So that's good. And we need slope. So for slope, well, we take our derivative, dy dx, evaluate it at 3, 1. So they take the derivative at that point. So we're going to take our expression here, and everywhere where we see an x, we put a 3. Everywhere where we see a y, we put a 1. So we're going to have a 2 minus 3 over, right, because x is 3, over 2 plus 4, because y equals 1. And so we get a minus 1 over 6. Minus 1/6. So point and slope. Well, now that we have that, we say, what's our formula? Well, there's a couple ways to do this. Y minus y naught equals mx minus x naught. That's a pretty good one. There's a few formulas, but let's start with this one. And we say, okay, what do we have? Well, we have our y minus 1, our y value, is equal to our slope, minus 1/6, x minus 3, our x value. And that's a fine way to leave the answer. I'll go ahead and just clean it up a little bit. Minus 1/6 times minus 3 is plus 3 over 6, which is also plus a half. And if I add 1 to both sides, we end up with y equals minus 1 over 6x. A half plus 1 is 3 halves. And there we go. That's our answer. Okay, well, that was fun. On to number 10. And in the interest of full disclosure, I recognize this problem. I wrote this one. And so if I'm going to curse anybody, it's going to be me. Curse you, Steve. But that's okay. That's all right. What do we have? A rubber inner tube in the shape of a torus, also known as a donut, is being inflated using an air pump that fills the tube at a constant rate of 1,000 pi squared inches cubed per minute. As the tube is filling, there is a monitor for the rates of change for the major radius of the whole tube, so that's this W, and the radius of one side of the tube, R, that's that value there. And the volume of a torus is given by V equals 2 pi squared R squared W. This is true. This is not just a random formula. This is actually how you compute the volume of a torus, or at least it's how you can. At a particular moment, we have W is 8 inches, dW dt is 4 inches per minute, and dr dt is 5 inches per minute. What is the volume? And notice here, they italicize that, emphasizing volume of the inner tube at that moment. Include units in your answer. Now, what kind of a question is this? Right? Think back. What do we see here? What are the clues? You know, we're the question whisperers. We're trying to hear what the question is telling us. What are we seeing? We're seeing rates, dW dt, dr dt, and there's even this rate up here. So when you see multiple rates, what problem are we in? Related rates. So this is a related rates problem. Okay, so we know we're going to be doing related rates. All right, well, that's just part of the story, though. Let's see what we need. We know we need to get volume. To compute volume, we need W, which we have, and we need R. Okay, so we kind of have a goal in mind. Find R. So how are we going to do that? Well, that's probably where we're going to have to dig into our related rates. So let's write down what we know. Now, we know a couple of things. We know W. Okay, so that's 8. I'm going to not put units in. Units have a way of working themselves out, right? Because we see the measurements and size are all in inches. Measurements and times are all in minutes. So we'll only worry about units at the end. So W equals 8. dW dt is 4. dr dt is 5. And all right, so we've gotten that term, that term, that term. But notice there's this one other expression. What is this? That's a number. And so oftentimes when I see a number in a math problem, I want to say, well, what is being represented here? So the air pump fills the tube at this rate. So that's the amount of air going into the tube, or the size of the air going into the tube. So what is this telling us? This is telling us how the volume is changing. dV dt, that's 1,000 pi squared. Okay, all right. So that's the list of what we know. And we have our relationship, 2 pi squared r squared w. So related rates, there should be a relationship. Sometimes we have to find it, and sometimes they give it to us. Never look a gift horse in the mouth. Now, with this, what are we going to do? Well, the idea is to think of everything as depending on time. So volume depends on time, r depends on time, and w depends on time. So we're going to take our derivative with respect to time. We get dv dt, derivative of v with respect to t. Well, 2 pi squared is a constant. And then we have this r squared w. So we have to do a product rule. The derivative of r squared, 2 comes down, r to the 1 times the derivative of r with respect to t, dr dt. The w stays as is, plus, right, derivative of the first, and then 2 pi squared, leave the first alone, times the derivative of the second, dw dt. Okay, so that's our setup. Now, what do? We plug in what we know. So what are things we know? We know dv dt, we know dr dt, we know w, we know dw dt. So those are things we know. So we're going to replace those values with what they are. So dv dt, 1,000 pi squared equals 4 pi squared r, and times dr dt, which is 5, times w, which is 8, plus 2 pi squared r squared times dw dt, which is 4. All right. It's all been laid out for us. So, what do we have? Well, we have a single equation with one unknown. We don't know what r squared is. So we start cleaning up. Now there's some things we can do. Everything has a pi squared, so that can help us make the computations a little bit simpler. And, let's rewrite this. We have 2 times 4 is 8r squared. Here we have plus, all right, as 8 times 20, because we have an 8 times 20r. And the 1,000, we'll move that across. It'll become a minus. And does 1,000, is that divisible by 8? Yes, it is. It's 8 times 125. And so we can get rid of all these 8s. 8 is enough. So we get r squared plus 20r minus 125 equals 0. All right, we're in the home stretch. does this factor? Well, we have to have faith in our teachers, right? They love us, and they want the best for us. So they're going to give us something that will either factor or it's going to be clean if you use the quadratic formula. So we think of 125, which is 5 times 5 times 5. So we have, okay, how can you write 125? Well, 1 times 125 or 5 times 25. That's it. Now, can we think of ways to combine 5 and 25 to get 20? It's like, oh yeah. If you do the following, if you did plus 25 minus 5, because what would happen? You get the r squared, which is good. Minus 5r plus 25r is 20r, minus 125, which leads us to r is negative 25, or r is positive 5. But one of these is nonsense, because r is a physical measurement. So we must have that r equals 5. Yes! Are we done? No. What? No, I thought we were celebrating. Yes, we are celebrating because we had a goal. The goal was to find r. But what does the problem ask us? It says, find the volume. Now, with our value for r, we can say, look, volume is 2 pi squared times r squared times w. All right, 2 pi squared r squared w. Well, 25 times 2 is 50, times 8 makes 400. So this becomes 400 pi squared. Now, are we done? Put a box around it. Is this the answer? And why not? Well, they also had another instruction. Include units in your answer. Oh, okay. So that's going to be like a point, right? And we're going to get that point. Oh, we deserve that point. So if we put units in here, what do we need? How do you measure volume? Now, all our measurements have been in inches. So a volume is going to be inches cubed, right? In inches by inches by inches. So inches cubed. And now we are done. That's our answer. Nice. All right. Well, as much as it'd be fun to reminisce about good times, we got to keep going. Number 11. The graph of the derivative of f of x, so this is f prime of x, is shown from negative 4 to 14. So we're told that this is the derivative, which is f prime. Here we're told y equals f prime of x. And each one of these says, recall that the graph above is f prime of x. And there's 3 of them, like, it's so small, it goes off the screen here. So they really are trying to remind us this is f prime. Okay, so with that in mind, we're ready. All right. So, A. Identify and classify each critical point of y equals f of x as a local minimum, a local maximum, or neither. Recall the graph above shows f prime of x. All right. Now, this is interesting because I'm trying to remember what to do. But okay. When I say it's interesting, what are we looking for? Well, what we're looking for is where are critical points. And so if we go by the book's definition, critical points is f prime equals 0 or f prime undefined. Now, the book does not include the endpoints, and so that's why I was like, do we include endpoints or not? So technically, if it just says critical points, we don't have to worry about endpoints. Now, endpoints are interesting, But for us, we won't worry about them. So, is the derivative ever undefined? Well, we look at the function and say, no. For every single value, we have a number. So the derivative is never undefined. So what do? Well, we look for the zeros. And we see 3 places. Okay, so we have at x equals -3, x equals +4, x equals 12. Okay, so that's the identify. But we got to do the classify. So, how do we classify? Well, we have the first derivative, so let's do first derivative test. So, what's first derivative test? Well, if you have let's say, positive, negative, that means you're going up, down. So then you have a local max. If you have negative, positive, down, up, you have a min. And if you have minus, minus, or plus, plus, right? So minus, minus, we go down, down, plus, plus, we go up, up. It's neither. So that's the first derivative test. So what are we looking at? Well, look at -3. So here we see derivative is negative, and then we see derivative is positive. So we're negative, then positive, going down, going up. So what kind of point do we have? It's a min. So this is a local min. Now at 4, well, we see we're positive and positive. Up, up. What are we doing? It is neither. Okay. And then our last one. Well, here we're positive, and then we're negative, right? Because we're positive above the axis, negative below the axis. So up, down, up, down. What are we? We are a local max. And there we go. Okay. On to part B. On what intervals is the function concave down? Recall, the graph above shows f prime of x. Okay, now we have to think about what does concave down mean? So concave down says, oh, your second derivative is negative. Okay, so that's what concave down means. Now, there's another way to say this. Concave down, this is the same as saying, think about it in terms of the first derivative. If the second derivative is negative, what does it say about the first derivative? It says your first derivative is decreasing. All right? First derivative decreasing means that the derivative of the derivative, second derivative, is negative. So, if we look at this, we say, okay, where in the graph are we going down? So we're going up, up, up. It's our moment until we get to here. Then, going down, 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 up. We're going up, up, up. Then down, down, down. So we're decreasing, and I would say from 0 up to x less than 4. So from 0 to 4, and from 8 to 14. Now, there's arguments. Should we include the endpoints or not? We won't test you in that fine detail. So the answer we are looking for, we are concave down on those intervals, because those are the intervals that corresponds where the derivative is decreasing. Okay. Nice. Now, part C. Identify the x-coordinate of all inflection points for y equals f of x. And recall, the graph shows f prime of x. So this actually is going to be easier than you think, right? Because we've done all the work. Because what happens is, if we come here, we're going up. So we're concave up. That's we're increasing, decreasing, concave down, increasing, concave up, decreasing, concave down. So our inflection points are where concavity changes. So we have 3 places where concavity changes. So we are at 0, at 4, and at 8. So the x-coordinates are x equals 0, x equals 4, x equals 8. And that's the answer. All right, because it didn't ask us to justify it. But if they had asked for justification, we would say things like, oh, here in part A, use first derivative test. In part B, this is where f prime is decreasing. In part C, we would say this is where we go from increasing to decreasing or decreasing to increasing. One of the, something very short and simple. All right, well, now with that out of the way, on to number 12. Solve the following differential equation. Okay, solve. Now, that means we want to get all the way to y. Okay, so how do we do it? Well, at this point, there's just one technique that we know. So that's going to make it really easy to us. Because if it says solve a differential equation, we're going to be like, well, we know how to do one thing, so we're going to do that thing. So what's our thing? And in particular, the one thing we know how to do is separable differential equations. So that's going to be what we need to do. Now, there's a 3-step process. And step 1, that's where it gets its name separable. We separate. Step 2 is after you separate, you integrate. And step 3, well, at least this is what I call it, you uncomplicate. And that's a very big word. I was going for the 888 kind of rhyming scheme. So what do we mean by separate? Well, we're going to put all the y's on one side, all the t's on the other side. So when it comes to y's, we see a dy and this y cubed. And let's go ahead and put the minus y cubed over. Minus has to go someplace. I have a gut feeling that the minus might be more helpful going with the y. Minuses, constants in general, you just move them wherever you like. Then the t, the dt and the te, the t squared, that's going to go to the other side. So in particular, what do we have? We have minus, and when we bring this across, we can think of this as 1 over y cubed dy, and that's going to be equal to, and what's on the other side? I'm going too much into my color scheme here. T e to the t squared dt. All right. So here we go. Here we go. So that's step 1. Check. Now we go into step 2, which is we integrate both sides. So for the left-hand side, we say, well, first, you can pull out the minus, and then we make this more calculus-friendly. So y to the negative 3 dy. In this format, we can read it off. We would add 1 to the exponent, which makes us y to the minus 2, and then we divide by that. So there's a minus and a minus a half, right? Divide by minus 2, multiply by minus a half. All right, now that minus minus makes a plus. Over here, Well, t e to the t squared, how do we handle that? We'll do a substitution, classic substitution here. We see a function on the inside, and so we'll let u equal t squared, and that says that du equals 2t dt, or 1/2 du is t dt. So this becomes what? This becomes the integral of 1/2 du e to the u, which, well, that's 1/2 e to the u, plus c, which is 1/2 e to the t squared, plus c. All right, now, let's clean up. We have 1/2, y to the minus 2 is 1 over y squared, equals 1/2 e to the t squared plus c. And we're going to do a little trick here, which is cancel the half. They might say, oh, but Steve, what about that plus c? Oh, so here's what I'm going to say to that. You might say, well, don't I need to like put a half there or multiply by 2 or something? And here's the thing. C is a constant. And constants are like sponges. They absorb other constants. So we're okay. We're okay. Now, what needs to happen next? We can do a couple of things here. We need to solve for c. So we can solve if we're comfortable with it. Let's go ahead and do that. And so we have 1 over y squared. Well, that's 1 over a half squared. So 1 over 1/2 squared equals e to the 0 plus c. Now, a half squared is a fourth, and 1 over that gives us 4. E to the 0 is 1 plus c. And then we can say, oh, well, that says c equals 3. Okay, so now we know c. So, getting back here, we have 1 over y squared equals e to the t squared plus 3. Well, we'll flip both sides because we're solving, right? Solve says we need to get y by itself. Okay, so there's currently, I need to get this so it just says y. So right now it's downstairs. If I flip, it moves up. So y squared is 1 over e to the t squared plus 3. And now take the square root. So y is 1 over the square root of e to the t squared plus 3. Now, there's a little subtlety that just happened, and I don't want to undersell it because it was an important thing. What did I forget to do? Or at least, what did I not write? We took the square root. Now, when you take a square root, what happens? Plus minus. So why did I not write plus minus? Well, one could say I should have. So let's go ahead and do that. I say, oh, I should have, so I'll do it. But now I can't have both. I need one. Which one do I need? And why is it the plus? Well, come back to your initial condition. I need it so that when I plug in t equals 0, I get out positive half. So initial condition tells us that we need the plus. Okay, so it says, lo and behold, our final answer for the solving is y equals 1 over the square root e to the t squared plus 3. Okay. Cool. Now, part B. Find the limit as t goes to infinity of y of t. Well, there's y of t. So we're saying find the limit as t goes to infinity of 1 over square root e to the t squared plus 3. And now, this is not meant to be complicated. We just say, let's think about it. What's going on? Well, this gets big. because it's e to a big thing. E to a big thing, big thing. Now, if it was e to a negative big thing, e to a negative big thing gets small. So pay attention. Sign matters. So this gets big, which means that what? You have a big thing plus 3, that's big. Square root of a big thing, big. 1 over a big thing, small. So what does this become? 0. And that's the answer. So it's not meant to be complicated. It's just plug it in, and you should just say, oh, what happens? And in this case, we didn't have to do anything fancy. We said, oh, that term downstairs is getting huge. 1 over a huge thing is going to 0. And so not all questions are meant to be complicated. All right, that brings us to our final problem. Number 13. If g of x is the integral secant x to 2x log t dt, find g prime of x. Okay, so what are we doing? We're taking a derivative of something which has an integral. Well, this problem sounds fun. Fundamental, right? It's the fundamental theorem of calculus. Woohoo! Nice. Now, what does the fundamental theorem of calculus say? There's a couple of ways to say it. In its most basic way, it says the following. If you take the derivative of the integral from a up to x of some function f of t dt, then what you get is f of x. And it's essentially saying if you integrate, it's sort of the opposite of doing a derivative. So derivative and integration are undoing each other in some sense. That's what it's trying to say. So that's why we call it fundamental, because it's tying two ideas together. The idea of finding a total with the idea of finding change. So that, finding one relates to finding the other. Okay, now that's the basic one. But we can kick it up a notch. So let's kick it up a little bit here. Suppose I said derivative of the integral from, let's say, a to g of x of f of t dt. Well, what happens here? Well, the answer is here we have a function g of x inside of another function, right? It's this function, but see, we're replacing the x by the g of x. So what do you use? The chain rule. So the outside function, when you take its derivative, is f of x. So what do we get? We get f, the outside, take rid of the outside, plug in the inside, g of x, times the derivative of the inside, g prime of x. Okay, so that's the next layer, right? So it's the chain rule plus fundamental theorem of calculus. Now, the last layer says, oh, what if you have let's say h of x to g of x of f of t dt? The answer? Well, you can split into parts and you flip one part upside down, but I'll go ahead and write it down. So this is the ultimate, in some sense, expression. It's f of g of x, g prime of x, minus f of h of x, h prime of x. All right. So those are your three layers of the fundamental theorem of calculus, as we get sort of from basic to chain rule plus chain rule twice, in some sense. Okay, so what setting are we in? That third one. So here we go. Here we go. We're ready to bring it home. So g prime of x, that's the derivative of integral secant of x to 2x, 2 to the power x, not 2 times x, it's 2 to the power x, pay attention, at log t dt. Okay, so according to the rule, we do what? Well, we take f, so here, f is log. So we're going to take the 2 to the x and plug it in. So that's going to be log of 2 to the power x times the derivative of 2 to the x. Now, what is the derivative in general of a to the power x? The answer is a to the power x log a. How does that follow? Well, that's because you can write a as e to the log a of x. So this becomes the derivative of e to log a times x. So e to something is e to that thing times the derivative of the inside. So that's where that log a comes from. Okay, so what do we get? So we plugged in 2 to the x and times that by the derivative of 2 to the x is 2 to the x ln 2. All right, so that's the first piece. Minus, right, because f gx times g prime of x minus ln of, now we're plugging the secant x in, so ln secant x times the derivative of secant, which is secant tangent. And we don't have anything else. There's no plus c because we're not integrating, we're differentiating. And that is a perfectly valid answer. Now, we could do a few other things. It doesn't say simplify as much as possible. We could, if we wanted to, say, hey, there's another way to write log 2x. That's x times log 2. And we have another log 2 there. So we could write this as x times 2 to the x times log 2 quantity squared. But we're not really gaining anything at that point. And so, you know what? We're okay to leave it as that is. And there you go. There we go. Okay, and that was our test. What a fun test. There were some subtle points up here, but it was a good practice. It's good practice. And so thanks for joining me. I hope this helps. Remember, your final will probably vary significantly in many details. That being said, there were a lot of good ideas, and things that we saw are likely to show up on the final. So, pay attention, practice, do your part so that you can succeed. Good luck, and I hope it goes well. All right. Bye.